What if there's a lot more to the universe than we currently understand? Imagine we're only scratching the surface of a much bigger mystery. Think about the beginning of everything, the cosmos and all the stuff in it that's hard to detect, like dark matter and dark energy. Science helps us uncover bits of the truth, but there's still so much we don't know. Join us as we delve into the most mind-blowing mysteries in the universe. The story of the universe's beginning is a fascinating journey into the depths of time, where scientific theories spark imagination and curiosity. At the forefront of this exploration is the Big Bang Theory, which posits that the universe began as an incredibly hot and dense point approximately 14 billion years ago. In an event of unimaginable energy and expansion, it suddenly erupted, causing space itself to stretch. This expansion continues today, leading to the vast, intricate cosmos we observe. Before the Big Bang, traditional concept of time and space become murky. Some scientists propose the idea that the universe could have existed in a state of singularity, where the normal laws of physics break down. This mysterious beginning, where everything was confined to a tiny, infinitely dense point, raises important questions about what might have preceded it. Another prominent perspective is the multiverse theory. This theory suggests that our universe could be just one of many, existing alongside an infinite number of other universes, each with its own unique properties and perhaps even different physical laws. If this concept is correct, it reshapes our understanding of reality and suggests that the universe is far richer than we can see. Additionally, some scientists explore cyclical models, which propose that the universe undergoes a series of expansions and contractions, continuously recycling itself in an eternal loop. In such a scenario, what we perceive as a beginning could just be one phase in an endless cycle of birth, death, and rebirth. These theories interact and compete with each other, each offering answers to fundamental questions while also leaving many mysteries unsolved. As we look to the cosmos, we uncover not just our universe's origins, but also invite deep inquiries into existence itself. Cosmic inflation presents a revolutionary perspective on the beginning of the universe, reshaping how we comprehend its origins. Traditionally, the Big Bang Theory proposed that the universe began as a hot, dense point that expanded over time. However, inflation suggests that during its earliest moments, the universe experienced a remarkable period of rapid expansion, much faster than the speed of light. Imagine a balloon that is blown up in an instant. It transformed from a tiny speck into a vast expanse. This swift expansion solves several puzzles associated with the early universe. Without inflation, scientists struggle to explain why different regions of the cosmos appear so uniform and similar despite being separated by vast distances. Inflation theorized that, once the universe inflated, these regions were once in close proximity, allowing them to equalize in temperature and density before drifting apart. Additionally, inflation provides insight into the large-scale structures we observe today, such as galaxies and clusters. The tiny fluctuations in density caused by quantum effects during the inflationary epoch acted like seeds, growing over time into the vast cosmic web we see now. This concept of fluctuations intertwines with the idea that the universe's structure emerged from randomness, highlighting a deeper connection between the minute and the cosmic. While cosmic inflation refines our understanding, it also introduces complexity. It suggests that many universes could exist, each with different properties, a concept known as a multiverse. This idea challenges the singularity of our universe and raises philosophical questions about what constitutes reality and our place within it. Cosmic inflation not only provides answers to long-standing questions, but also opens a door to new inquiries, transforming how we think about the universe's beginning and the vast, mysterious fabric of existence itself. The Big Bang Theory marks the beginning of our universe, a moment when everything we know emerged from an incredibly hot, dense state. Despite its established prominence in cosmology, significant mysteries surround this monumental event and its early moments. To start, the exact condition of the universe at the very moment of the Big Bang remains largely enigmatic. Scientists believe that the universe began expanding rapidly, but the precise mechanics of how everything evolved during those first instances, when temperature and density were unimaginably high, are still poorly understood. This period encompasses what is known as cosmic inflation, a theory suggesting a swift expansion that occurred mere moments after the initial event. However, the details of this process and what may have triggered it remain hypothetical, leaving many questions unanswered. Another profound mystery lies within the formation of the fundamental forces and particles. In those early moments, the universe was a chaotic soup of energy, and as it cooled, particles began to form, transitioning from energy to matter. The unification of the forces, gravity, electromagnetism, and the strong and weak nuclear forces, during this time is a topic of intense study. We lack a complete understanding of how these forces develop their distinct characteristics and roles in shaping the universe we inhabit now. Moreover, the period following the Big Bang, known as the radiation era, is somewhat obscured in our current theories. The rapid expansion led to cooling, which allowed protons and neutrons to combine into light elements like hydrogen and helium. However, the exact processes that govern this nucleosynthesis are still being explored. The abundance of these elements hints at a finely tuned balance of conditions present during that era, but our grasp of this phenomenon is still developing. Dark matter and dark energy introduce additional layers of complexity to the narrative of the universe's early history. We know that most of the universe is comprised of these elusive substances, which do not interact with light and thus remain invisible. Their presence is inferred from gravitational effects, but their roles and origins remain a puzzle that haunts cosmologists. Finally, the cosmic microwave background radiation, an afterglow of the Big Bang, offers a glimpse into the universe's infancy. This faint radiation is a relic from when the universe became transparent to light. Studying it has revealed crucial information, yet it continues to unveil mysteries about the initial conditions of the cosmos and the uniformity seen throughout the universe today. In conclusion, while the Big Bang Theory provides a fascinating framework for understanding the universe's origins, it is far from complete. Each aspect, from cosmic inflation and the formation of fundamental forces to the nature of dark matter and the remnants of the cosmic microwave background, poses intriguing questions that challenge our knowledge and inspire ongoing research in the field of cosmology. The universe, despite its chaotic beginnings, exhibits a remarkable uniformity that can leave many pondering how such order emerged from what seemed like a tumultuous explosion. Scientists explain this phenomenon through a theory known as cosmic inflation. Imagine the universe as a balloon that, in its infancy, underwent a rapid expansion. In this early stage, the universe expanded faster than the speed of light, smoothing out irregularities and making the distribution of matter and energy more uniform. This swift expansion meant that any initial variations in temperature and density caused by quantum fluctuations in the very early moments were stretched and flattened across vast distances. As the universe continued to expand, these tiny imperfections remained, but they became statistical fluctuations rather than dramatic differences. Furthermore, as matter began to clump together under the influence of gravity, it organized into the structures we observe today, like galaxies and clusters of galaxies. Over billions of years, while local environments may appear chaotic, on a grand scale, the universe shows patterns and structures that reflect this initial state of smoothness. Also, the laws of physics, particularly thermodynamics and gravity, play essential roles in establishing this uniformity. Gravity tends to pull matter together, while thermodynamics dictates how energy disperses. Together, they foster a balance that supports the orderly distribution of galaxies across the cosmos. The universe's uniformity is a glimpse into its peaceful aftermath, smoothed by rapid expansion and shaped by fundamental forces, turning chaos into the harmonious cosmos we observe today. Dark matter is one of the universe's greatest mysteries. It is a substance that does not emit, absorb, or reflect light, making it completely invisible to our telescopes and sensors. Despite its elusive nature, scientists have strong evidence suggesting that dark matter constitutes a significant portion of the universe's total matter. Imagine the universe as a massive cosmic tapestry, where the visible stars and galaxies are like highlights in a broader fabric that remains unseen. Scientists have attempted to detect dark matter through various methods, including underground experiments designed to catch rare interactions with ordinary matter and observations of cosmic phenomena. Yet, it remains stubbornly out of reach, largely because the known particles that we typically study do not account for it. This uncertainty fuels ongoing research in the horizon, where scientists explore candidates for dark matter particles, which may only interact through gravity. Each breakthrough brings new insights, but the question of its composition and exact nature continues to elude our understanding, keeping dark matter as one of the most fascinating enigmas in modern astrophysics. Dark matter plays a crucial role in shaping the universe, particularly in the formation and structure of galaxies. Imagine a traditional scale. The visible matter in galaxies, which include stars, gas, and dust is only a fraction of what actually exists. Dark matter, which does not emit light or energy, acts like an invisible frame, holding everything together. As galaxies form, they draw in surrounding mass through gravitational attraction. The presence of dark matter creates a gravitational field that exercises a strong influence on visible matter, pulling it toward the centers of galaxies. This is essential because visible matter alone would not have enough gravitational pull to bind galaxies effectively, leading them to be less stable and prone to disintegration or dispersal. The distribution of dark matter within and around galaxies is often shaped like a halo, extending far beyond the visible parts. This dark matter halo influences how galaxies rotate. To visualize this, think of a carousel. While the outer horses should be moving slowly because they are farther from the center, they actually spin at similar speeds to those near the center. This unexpected behavior implies that there is much more mass present than what we can see, and that mass must be due to dark matter. Moreover, dark matter plays a pivotal role in galaxy collisions and interactions. When two galaxies meet, the gravitational tug-of-war is influenced significantly by the surrounding dark matter. Its overwhelming presence helps channel and guide the merger process, impacting the resultant structure and evolution of the new galaxy that emerges. Without dark matter, the universe would look entirely different. It provides a structural backbone that allows galaxies to form, grow, and evolve, acting as a silent but powerful force that shapes the very fabric of cosmic architecture. Dark energy is often referred to as one of the greatest mysteries in modern cosmology due to its elusive nature and the profound implications it has on our understanding of the universe. Imagine our universe as a vast, ever-expanding landscape. While we can see galaxies moving away from us, indicating that space itself is stretching, the reason for this acceleration is tied to dark energy. This enigmatic force is thought to make up a significant portion of the universe's total energy content, much more than both normal matter and dark matter combined. However, scientists have been unable to directly observe dark energy or comprehend its fundamental properties. It behaves in a way that is counterintuitive to our understanding of gravity and matter. Instead of pulling objects together, dark energy seems to push them apart, driving the accelerated rate of expansion. One of the biggest challenges is that, unlike ordinary matter or radiation, dark energy does not interact through any of the known forces. That's why it remains so undetectable. Its effects are felt on cosmic scales, over vast distances and immense time scales, which makes experiments and observations incredibly complex. Theories attempting to explain dark energy range from the possibility that it is a property of space itself to ideas involving modifications to our understanding of gravity. Each theory offers a different glimpse into the nature of the universe, but none have yet provided a definitive answer. Consequently, grappling with dark energy not only challenges the foundations of physics, but also invites questions about the ultimate fate of our universe. Will it continue to expand forever, or is there a limit to this growth? The search for answers continues, making dark energy a profound and captivating subject of cosmological inquiry. Detecting and studying dark matter, that mysterious substance thought to make up a significant portion of the universe, is one of the biggest challenges in modern astrophysics. Scientists believe dark matter does not emit light and can only be observed through its gravitational effects on visible matter. To uncover its secrets, researchers are employing several innovative approaches. One way scientists look for dark matter is through large underground detectors. These facilities are designed to catch rare interactions between dark matter particles and ordinary matter. Imagine an incredibly sensitive watch that records the faintest of movements. These detectors use materials that can produce small flashes of light or tiny electrical signals when a dark matter particle collides with an atomic nucleus. The hope is that, although these interactions are extremely rare, they can eventually be captured and understood. Another method involves observing galaxies and galaxy clusters. The influence of dark matter becomes evident in the way galaxies move. Scientists have attempted to detect dark matter through various methods, including underground experiments designed to catch rare interactions with ordinary matter and observations of cosmic phenomena. Yet, it remains stubbornly out of reach, largely because the known particles that we typically study do not account for it. This uncertainty fuels ongoing research in the horizon, where scientists explore candidates for dark matter particles, which may only interact through gravity. Each breakthrough brings new insights, but the question of its composition and exact nature continues to elude our understanding, keeping dark matter as one of the most fascinating enigmas in modern astrophysics. Dark matter plays a crucial role in shaping the universe, particularly in the formation and structure of galaxies. Imagine a traditional scale. The visible matter in galaxies, which includes stars, gas, and dust, is only a fraction of what actually exists. Dark matter, which does not emit light or energy, acts like an invisible frame holding everything together. As galaxies form, they draw in surrounding mass through gravitational attraction. The presence of dark matter creates a gravitational field that exercises a strong influence on visible matter, pulling it toward the centers of galaxies. This is essential because visible matter alone would not have enough gravitational pull to bind galaxies effectively, leading them to be less stable and prone to disintegration or dispersal. The distribution of dark matter within and around galaxies is often shaped like a halo, extending far beyond the visible parts. This dark matter halo influences how galaxies rotate. To visualize this, think of a carousel. While the outer horses should be moving slowly because they are farther from the center, they actually spin at similar speeds to those near the center. This unexpected behavior implies that there is much more mass present than what we can see, and that mass must be due to dark matter. Moreover, dark matter plays a pivotal role in galaxy collisions and interactions. When two galaxies meet, the gravitational tug-of-war is influenced significantly by the surrounding dark matter. Its overwhelming presence helps channel and guide the merger process, impacting the resultant structure and evolution of the new galaxy that emerges. Without dark matter, the universe would look entirely different. It provides a structural backbone that allows galaxies to form, grow, and evolve, acting as a silent but powerful force that shapes the very fabric of cosmic architecture. Dark energy is often referred to as one of the greatest mysteries in modern cosmology due to its elusive nature and the profound implications it has on our understanding of the universe. Imagine our universe as a vast, ever-expanding landscape. While we can see galaxies moving away from us, indicating that space itself is stretching, the reason for this acceleration is tied to dark energy. This enigmatic force is thought to make up a significant portion of the universe's total energy content, much more than both normal matter and dark matter combined. However, scientists have been unable to directly observe dark energy or comprehend its fundamental properties. It behaves in a way that is counterintuitive to our understanding of gravity and matter. Instead of pulling objects together, dark energy seems to push them apart, driving the accelerated rate of expansion. One of the biggest challenges is that, unlike ordinary matter or radiation, dark energy does not interact with any of the known forces. That's why it remains so undetectable. Its effects are felt on cosmic scales, over vast distances and immense time scales, which makes experiments and observations incredibly complex. Theories attempting to explain dark energy range from the possibility that it is a property of space itself to ideas involving modifications to our understanding of gravity. Each theory offers a different glimpse into the nature of the universe, but none have yet provided a definitive answer. Consequently, grappling with dark energy not only challenges the foundations of physics, but also invites questions about the ultimate fate of our universe. Will it continue to expand forever, or is there a limit to this growth? The search for answers continues, making dark energy a profound and captivating subject of cosmological inquiry. Detecting and studying dark matter, that mysterious substance thought to make up a significant portion of the universe, is one of the biggest challenges in modern astrophysics. Scientists believe dark matter does not emit light and can only be observed through its gravitational effects on visible matter. To uncover its secrets, researchers are employing several innovative approaches. One way scientists look for dark matter is through large underground detectors. These facilities are designed to catch rare interactions between dark matter particles and ordinary matter. Imagine an incredibly sensitive watch that records the faintest of movements. These detectors use materials that can produce small flashes of light or tiny electrical signals when a dark matter particle collides with an atomic nucleus. The hope is that, although these interactions are extremely rare, they can eventually be captured and understood. Another method involves observing galaxies and galaxy clusters. The influence of dark matter becomes evident in the way galaxies move. If we consider a group of stars moving around a galaxy, their speeds reveal that there must be more mass present than we can account for with visible matter alone. By studying the motion of these celestial bodies, scientists can infer the distribution of dark matter within those galaxies. Furthermore, scientists are also exploring the possibility of creating dark matter particles in high-energy particle collisions. Large particle accelerators, like those at CERN, smash particles together at incredible speeds, allowing researchers to probe the fundamental building blocks of matter. In this controlled environment, some hope to produce dark matter particles, providing direct evidence of its existence. Finally, astrophysicists observe the cosmic microwave background radiation, an ancient afterglow from the Big Bang. By examining fluctuations in this radiation, scientists can gain insights into how dark matter influenced the formation of structures in the early universe. This method helps paint a broader picture of the cosmos and how dark matter fits into its grand design. As researchers strive to unravel the mysteries of dark matter, these various methods contribute to a multifaceted approach in what promises to be a groundbreaking quest in our understanding of the universe. Each discovery brings scientists one step closer to revealing the elusive nature of this invisible substance that shapes our reality. Dark energy represents one of the most intriguing mysteries in modern astrophysics. Traditionally, gravity, as described by Newton and later refined by Einstein, is a force that attracts objects toward one another. In the framework of our universe, it was expected that this attractive force would result in a slowing down of the expansion of the cosmos over time due to gravitational pull. However, observations suggest otherwise. Data indicates that the universe is not only expanding but is accelerating in that process. This unexpected behavior introduces a concept of dark energy, a force that seems to counteract the effects of gravity on a grand scale. Imagine blowing up a balloon. As you blow air into it, the balloon expands, reflecting how the universe is stretching out. If gravity was solely at play, we might expect the air inside to pull the sides inward, slowing the expansion. Instead, dark energy acts like an unseen hand, pushing the balloon outward even faster. The challenge lies in understanding what dark energy actually is. It makes up a significant portion of the universe's total energy content, yet it interacts with matter in a way that is still unclear. Einstein introduced the cosmological constant a century ago as a way to explain a static universe, but discarded it once it was revealed the universe is expanding. Now, it appears that maintaining a cosmological constant might be closer to the truth. This constant represents a steady energy density filling space, pushing everything apart in a uniform manner. As scientists delve deeper into this conundrum, they confront profound implications for the nature of gravity itself and the fundamental structure of the universe. The existence of dark energy suggests that our understanding of gravity and its role in cosmic evolution is not complete. It challenges us to rethink how forces interact on both macroscopic and microscopic levels, pushing the frontier of physics into areas of theoretical speculation, particularly regarding the very fabric of space and time. The quest to unravel dark energy could very well lead to a new chapter in our grasp of the cosmos. According to some models, the inside of a black hole could be a region of warped space-time where time behaves differently than in our familiar universe. Some suggest that traveling through a black hole might even lead to other dimensions or parallel universes, opening the door to possibilities that were once purely science fiction. Moreover, researchers are exploring the hint provided by gravitational waves, ripples in space-time created by massive events such as black hole mergers. These observations may help reveal more about the fundamental structure and behaviors inside a black hole, shedding light on their enigmatic nature. As our understanding evolves, so too do our theories, weaving complex tapestry of notions that intertwine gravity, quantum mechanics, and the very fabric of reality. The ultimate truth may still be beyond our grasp, but every new discovery brings us a step closer to understanding the true nature of black holes and their intriguing secrets. Black holes represent one of the universe's most intriguing mysteries, particularly in how they intersect with the principles of quantum mechanics. The foundation of this connection lies in the nature of black holes themselves. When a star collapses under its own gravity, it forms a black hole, creating a region of space where gravity is so intense that not even light can escape. This seems to lead to a contradiction when considering what happens to information, which is critical in quantum mechanics. The information paradox arises from the idea that anything falling into a black hole appears to be lost forever. According to quantum mechanics, however, information cannot simply vanish. It must be conserved. This contradiction creates a persistent puzzle in physics. If black holes can swallow up information, where does that information go, and how does it reconcile with the laws of quantum theory? Scientists have proposed various theories to unravel this paradox. One intriguing concept is the idea of black hole evaporation, introduced by the physicist Stephen Hawking. He theorized that black holes can emit radiation, now known as Hawking radiation, causing them to gradually lose mass and eventually disappear. If this process occurs, it poses a question: does the information get lost forever when the black hole evaporates, or is it somehow preserved and released as a black hole shrinks? Several physicists propose that the information might be encoded at the black hole's event horizon, the boundary beyond which nothing can escape. This idea suggests that everything that falls into a black hole leaves a sort of imprint at the edge, potentially allowing for the recovery of information over time. These theories delve deeply into the fabric of space-time, suggesting that our understanding of gravity, time, and information is limited, and that further investigations could change how we comprehend the universe. As research in both astrophysics and quantum mechanics continues, the interaction between black holes and the principles of quantum theory remains a dynamic field of study, holding the potential to inform us about the fundamental structure of reality itself. Black holes play a crucial role in the evolution of galaxies, acting as both engines of growth and sources of destruction within galactic environments. At the heart of many galaxies lies a supermassive black hole, which can be millions to billions of times heavier than our Sun. These black holes influence our galaxies in several significant ways. First, as matter spirals inward toward a black hole, it forms an accretion disk, heating up and radiating energy. This process can release immense amounts of energy, impacting star formation in the surrounding regions. In fact, the energy output from these disks can either stimulate the creation of new stars or, conversely, suppress star formation by blowing away gas and dust that would otherwise coalesce into stars. This balancing act between star formation and energy output is vital in determining the structure and future of a galaxy. Additionally, the gravitational pull of supermassive black holes affect the orbits of stars and gas in their vicinity. This intense gravitational environment can lead to complex interactions, including the merging of smaller galaxies into larger ones. As galaxies collide, their central black holes may come together, eventually forming even larger black holes. The merging of galaxies, complemented by this process, plays a significant role in the growth of galaxies over cosmic time. Moreover, black holes influence galactic dynamics through powerful jets. When black holes consume material, they can eject it at near-light speeds in the form of jets that shoot out into space. These jets can impact surrounding gas clouds, further influencing star formation and the overall evolution of the galaxy's structure and star population. Black holes are not merely dormant cosmic monsters. They are active participants in the cosmic ballet of galactic evolution, shaping the interactions and growth of galaxies, impacting star formation, and driving the complex dynamics of our universe. Neutron stars are truly remarkable because they represent one of the universe's most extreme states of matter. Formed when massive stars exhaust their nuclear fuel and collapse under their own gravity, these celestial objects are incredibly dense. Picture compressing the mass of a sun into a sphere roughly the size of a city. This extraordinary density means that a single teaspoon of neutron star material would weigh as much as an entire mountain on Earth. What sets neutron stars apart even further is their composition. They are primarily made up of neutrons, which are subatomic particles that, alongside protons, form the nucleus of atoms. In a neutron star, the gravitational forces are so intense that electrons combine with protons to form neutrons, creating a unique state of matter known as neutronium. This extremely dense material gives neutron stars their incredible gravitational pull. Additionally, many neutron stars are observed as pulsars, which are rapidly spinning stars that emit beams of radiation as they rotate. These beams sweep across space like lighthouse beacons. The remarkable speed of their rotation can reach hundreds of times per second, generating immense electromagnetic fields. This pulsating behavior allows astronomers to study their properties in great detail, offering insights into fundamental physics and the fabric of the universe. Neutron stars also serve as natural laboratories for studying the interactions of matter under extreme conditions. Their existence challenges our understanding of physics, particularly in fields like quantum mechanics and general relativity. Thus, neutron stars not only showcase the incredible diversity of celestial bodies, but also push the boundaries of our knowledge about the universe itself. Magnetars, a type of neutron star, possess incredibly strong magnetic fields, about 1,000 times stronger than those of ordinary neutron stars. To understand these cosmic oddities, scientists employ a combination of observational techniques and theoretical models. Astronomers often look to the electromagnetic spectrum, especially in the X-ray and gamma-ray ranges, to study magnetars. These regions of light can penetrate dense materials and provide insights into the magnetar's energetic emissions. By observing bursts of radiation that magnetars emit, scientists can infer details about their magnetic fields. For instance, the energy and frequency of these emissions offer clues about the strength of the magnetic field and its effects on the surrounding matter. Additionally, scientists utilize telescopes equipped with advanced detectors to capture these fleeting bursts. Telescopes on Earth and in space, combined with powerful observational techniques, allow researchers to track these events in real time. Different observations are cross-referenced to build a comprehensive understanding of a magnetar's magnetic activity and its effects on the environment around it. The magnetic fields also impact how these stars spin. By studying the rotation rate and any changes in it, researchers gain further insights into the internal structure of the magnetar. Through a combination of direct observation and mathematical modeling, scientists can piece together the mysteries of these extraordinary objects. Even without being able to travel to them directly, by integrating data from multiple sources and refining their theoretical frameworks, scientists continue to unravel profound effects that magnetars have on their surroundings and the fundamental physics at play in the universe. The very fabric of space-time, each collision serves as a cosmic laboratory that contributes to our knowledge of extreme physics, helping to piece together the landscape of the universe and our origins within it. The combination of gravitational wave data and light observed from COVID now helps reveal the mysteries of how the universe functions on a grand scale. As such, these discoveries are only the beginning, promising vast insights into the universe's most powerful and enigmatic processes. The idea of extra dimensions beyond our perceivable universe has captured the imagination of scientists and laypeople alike. One of the most prominent concepts arises from string theory, which suggests that the fundamental building blocks of the universe are not point-like particles, but rather tiny vibrating strings. These strings can oscillate in multiple ways, but in order for the full range of their behavior to exist, additional dimensions beyond familiar 3 dimensions of space and 1 dimension of time are necessary. The theory typically proposes that there are 6 or 7 extra dimensions curled up and hidden from our direct observation, making them incredibly challenging to detect. Another intriguing framework is that of brane-world cosmology, which stems from string theory as well. In this view, our observable universe could be likened to a 3-dimensional surface, or brane, floating within a higher dimensional space. Events occurring in these additional dimensions might influence the physical laws and phenomena we experience, even if we cannot directly observe them. Additionally, some theories in theoretical physics, like quantum gravity models, explore the implications of more than 4 dimensions by examining how gravity might behave differently when considered in a higher dimensional context. These models seek to reconcile the seemingly separate realms of quantum mechanics and general relativity, hinting that our universe may be part of a more complex structure than we can currently perceive. Finally, ideas such as multidimensional landscapes in cosmological theory suggest that our universe is just one of many possible configurations existing within a higher dimensional space, akin to a bubble among countless others. Each of these bubbles could have distinct physical laws and constants, further broadening the scope of what we might view as our reality. These theories push the boundaries of our understanding, proposing that the universe may be far more intricate than our everyday experiences suggest, encouraging scientists to explore the nature of existence beyond the limits of current perception. The concept of extra dimensions suggests that there are more spatial dimensions beyond the 3 we experience daily. Traditionally, we understand space as having length, width, and height, but theories in physics, notably string theory, propose the existence of additional dimensions that could be compacted or hidden from our view. This idea fundamentally alters our understanding of the universe and the laws governing it. Picture the familiar 3-dimensional world. Now, imagine that there are additional dimensions curled tightly, so small that they escape detection at our scale. These extra dimensions can influence the fundamental forces and particles we observe. For instance, they can provide new pathways for gravity to strengthen or weaken, potentially explaining why gravity seems so weak compared to other forces like electromagnetism. In a universe with extra dimensions, gravity could disperse into these dimensions, making it less potent in our familiar 3-dimensional space. Moreover, the presence of extra dimensions could lead to new particles and interactions, modifying the standard model of particle physics. Such changes might help us understand phenomena like dark matter or dark energy, which remain elusive in current theories. When particles are allowed to move in additional dimensions, their behaviors could shift dramatically, offering explanations for things we cannot yet fully explain. Extra dimensions might also provide insights into the early universe, particularly during events like the Big Bang. The conditions of that time could have triggered interactions that played out differently based on how many dimensions were involved. In this sense, extra dimensions might not only affect current laws but could also reshape our understanding of the universe's history and its ultimate fate. By exploring these hidden dimensions, we venture into uncharted territories of physics, where the established rules of reality bend and twist, opening possibilities for new physics that could one day rewrite our definition of the cosmos. Scientists are venturing into the mysterious territory of extra dimensions, guided by theories that suggest our universe might have more spatial dimensions than the three we experience daily. One primary approach involved particle colliders like the Large Hadron Collider. Here, protons are accelerated to nearly the speed of light and smashed together. When they collide, these experiments unleash vast amounts of energy, which can, in theory, create tiny black holes or other particles that reveal the existence of extra dimensions. If these phenomena appear in the data collected, it could be a groundbreaking confirmation of higher dimensions. Another avenue of exploration involves gravitational wave detection. When two massive objects, such as black holes, collide, they produce ripples in space-time. By studying these waves, scientists hope to uncover anomalies that suggest the influence of extra dimensions on gravity and how it behaves. The existence of additional dimensions could alter the characteristics of these waves, providing crucial hints about their presence. Additionally, researchers are investigating certain types of cosmic rays and their interactions in the atmosphere. When high-energy particles from space collide with atoms in the Earth's atmosphere, they can produce showers of secondary particles. Analyzing these interactions might provide indirect evidence for extra dimensions if the results consistently deviate from expected patterns. All of these experiments share one critical goal: to provide a deeper understanding of the fundamental fabric of the universe. By identifying signs of extra dimensions, scientists could reshape our perception of reality, bridging gaps between known physics and the unknown realms that lie beyond our familiar three-dimensional world. Extra dimensions play a pivotal role in string theory, which is a leading framework attempting to unify our understanding of fundamental forces and particles. To grasp their significance, envision our familiar three-dimensional world, where we can move left, right, forward, backward, up, and down. However, string theory proposes that the universe might have more dimensions, usually posited as additional hidden dimensions are compactified, meaning they are curled up so small we can't perceive them in everyday life. These extra dimensions are essential for several reasons. First, they provide the necessary framework for strings, which are the fundamental building blocks in string theory. In this view, particles are not point-like objects, but rather tiny vibrating strings. The different vibrations of these strings correspond to different particle types, similar to how the strings on a musical instrument produce various notes. The properties of these particles, including mass and charge, are influenced by how these strings interact with the extra dimensions. Moreover, extra dimensions help reconcile gravity with the other fundamental forces. In our four-dimensional perspective, 3 dimensions of space and one at a time, gravity behaves differently compared to forces like electromagnetism. By incorporating additional dimensions, string theory offers a more comprehensive picture where gravity can be described alongside other forces, potentially addressing phenomena that current models cannot explain, such as the behavior of black holes or the conditions of the very early universe. Additionally, hidden dimensions may provide clues about why our universe appears fine-tuned and why certain constants of nature have the values they do. These extra dimensions enrich the fabric of string theory, giving it the flexibility to model the complexities of our universe, consequently paving the way for a deeper understanding of the cosmos. The idea of extra dimensions opens up a fascinating new perspective on the structure of the universe. Traditionally, we experience a world in 3 spatial dimensions.
The Big Bang
length,
did not bang.
width, and
It
height
did not explode.
plus time.
It was
However,
not a bomb.
Theory
It was
suggests
not a
that beyond
detonation
these familiar
or
dimensions,
conflagration.
there
There
could
was
be
no
additional
blast,
ones intricately
no
woven
debris,
into the fabric
no
of
shrapnel.
reality. The
Imagine
universe
our
was simply
three-dimensional
smaller in the
world
past,
as a sheet of
and
paper,
it will be bigger
flat
in the future.
and straightforward.
And that is not the
If
only
extra
misconception
dimensions
you may
exist,
have about the
they
Big
might
Bang.
be like folds
To
or
begin
wrinkles
with,
on that paper.
the Big Bang
hidden
didn't
from our
happen
direct
anywhere.
view, yet
It
influencing
happened
everything
everywhere.
we see.
It was not
These
an event
extra
in space,
dimensions could be
but
compact
rather
and
an
curled
event
up
in
so
time.
small that they remain
It was a
unnoticed
tick on
in
a
our
clock,
daily lives.
not the
While
notch
they
in
might
a
act
ruler.
as pathways
It occurred
connecting
in the
different
finite
points in our
parts of
universe.
everything in the cosmos. Every atom, every particle, every point can trace its evolutionary origins back through the eons to the Big Bang. The Big Bang happened in the room you're in right now. It happened in the Andromeda Galaxy. It happened inside you. It happened within the entire expanse of the known and unknown universe. The entire universe was smaller, hotter, and denser in the past. Now it's not. That is the great lesson of the Big Bang. And so, the universe has no center and no edge. It expands from nowhere and expands to nowhere. The universe did not originate from a single point in space. The Big Bang was a point from which space originated. In these statements lies an inconsistency, a paradox. 13.787 billion years ago, our theories tell us that the universe, the entire universe, regardless of its size, even if infinite, was contained somehow in a singularity, a point of infinite density and no spatial extent. But this makes no sense. This does not obey the rules of reason or logic. And this is because the Big Bang singularity is not a true representation of what everything was. It is simply a heavy hint that our equations, our math, our physics are dysfunctional. The singularity is a sign that we do not understand our origins, the earliest moments of the Big Bang. But in the darkness of that uncertainty is nature the seed of a new awakening. For in our ignorance of the Big Bang, we have the opportunity for now, only seen as a ghost and whispers of mercilessly complicated mathematics, to pierce the veil of our own beginning, to try and deduce what came before the birth of everything. Because at one time, there was no universe. And then there was. This is a mystery of creation, the paradox of our reality, revealed by the existence of the expansion of the universe. But was that beginning truly the beginning? Did time start with the Big Bang? Did our universe come into existence only at that moment, or was there something before, either similar to our cosmos, or entirely different? If the Big Bang was the beginning of everything that we know, was it also the beginning of literally everything? Or is our universe just a small part of a grander fabric, a greater story that has been told since the distant ages of time past, and will continue to exist well after our cosmos has sunk into cold oblivion? In 2022, incredible results started to arrive from the new James Webb Space Telescope, but rumors online and in the press started to spread that they were a death knell for the Big Bang theory. Of course, this was not the case and served as a great example of the importance of media literacy, which is why I'm excited to have Ground News kindly sponsor this video. Ground News aggregates the world's news in one place so you can compare coverage and verify your information, and it's been a big help in my research. For example, last month solar storms were reported to disrupt communication and produce northern lights as far as the southern US. On Ground News, I was able to access over 200 articles published on this. At a glance, nearly 90% were from sources rated highly factual, indicating coverage is less subjective, which is important for science news. Comparing coverage is also interesting. NPR suggested the storm disrupted communications, while the majority of the sources, including F.org, emphasized the northern lights and no serious problems. And so, if you're looking for a better way to get the full picture, I encourage you to visit ground.news or subscribe through my link to save 40% off unlimited access. By subscribing, you're not only supporting the channel but transparency in the media as well. Before the Big Bang, well, it was 2013 and it was time to party. The attendees gathered in the main hall of the Paris Observatory, a ground building situated on the south side of Paris, near the old gates to the city. People got up to speak to congratulate each other on the successful mission and a job well done, including some remarks that there was, of course, more work to be done in the coming months. But before anyone could dwell too much on the task ahead, they marveled as cases were brought out from a back room. The cases were full of champagne, but not just any champagne. The organizers of the party had commissioned a special bottling, and the bottles had custom labels. On each bottle was printed an oval disc with an odd speckled pattern. That pattern was the cosmic microwave background, or CMB, a background radiation from just after Big Bang that fills the entire universe. The European Space Agency's Planck satellite had collected the data to construct that image, the highest resolution all-sky image of the CMB ever made. The Partagoes were celebrating the first public release of the Planck satellite data, and they had every reason to celebrate. The data taken by Planck had confirmed the existing cosmological model and the story of the Big Bang. And on top of this, it had found evidence that the theory of inflation, a hypothetical event where the very early universe grew exponentially larger in a short amount of time, was on the right track. The Big Bang wasn't really a Big Bang. What we call the Big Bang, a name coined somewhat derisively by astronomer Fred Hoyle, is really just a generic description of the model of the universe, where our cosmos used to be small in the past and will be larger in the future. In this model, there really isn't an explosive event that launches the creation of the universe, or a swift unfolding of space that gives rise to everything we know. Instead, it's much simpler. It is just a mere expansion from a smaller state to a bigger one, and from that theory, we can assign a number, 13.787 billion years, with an uncertainty of 0.02. A simple number, but this number is special. It's our current best estimate, in billions of years, of the age of the universe. Indeed, a direct consequence of the Big Bang theory is that there was a time before time. There was a moment when the universe simply became, and that moment existed 13.787 billion years ago. But that's only the dimension of time as far as we know. The three dimensions of space that also make up our universe could be infinitely big. Yes, there's a limit to our observable cosmos, a boundary set by the finiteness of the speed of light. That limit sits about 45 billion light-years away. Beyond that, we presume that there's more universe, more stars and galaxies and gas and dust. But we don't know. It could be infinite, but not in the direction of time. Our universe could live infinitely into the future, even when our cosmos expands so far and so much that all the stars die out and existence is nothing more than a thin soup of particles near a temperature of absolute zero. The universe will still exist. Time will still march forward. Directions in space will still be in place. But the past is different. There is a limit to what we perceive, a boundary of our understanding. Even if the universe is infinitely big and will extend forever into the future, it all came from something. This simple, straightforward Big Bang model has been able to explain a wealth of observational data, like the apparent recession of galaxies away from us, the appearance of the cosmic microwave background, even the amount of light elements in the cosmos. In fact, no other cosmological theory is able to explain the existence of all those facts. But just like any other scientific theory or model, the Big Bang also has its shortcomings. And in 1979, physicist Alan Guth was poking at one of those shortcomings. In most theoretical models of the extremely early universe of the time, the cosmos seemed to naturally produce a significant number of defects, things like magnetic monopoles, cosmic strings, and other bizarre intergalactic warpings of space and time. However, none of these oddities had ever been observed in the real universe. And so, Guth was trying to find a way to get rid of them. In a stroke of pure imagination, he wondered if the Big Bang really was a little more like its namesake than we previously suspected, a little banger. And so, he proposed a new entity to inhabit the cosmos, something called a scalar field. Scalar fields were not a new idea in physics. Quantum field theory, which, alongside Einstein's general theory of relativity, underlies our understanding of reality, is strange. Everything that exists, every particle and every form of radiation, is really the manifestation of an underlying quantum field that fills a universe. These quantum fields soak space and time the same way that olive oil and vinegar soak a piece of bread. Every particle has its own associated field, one for the photon known as the electromagnetic field, one for the electron known as the Dirac field, and so on and so on. When one of these quantum fields has a local excitation, a region of higher energy vibrations, we see that as an independent particle. But of course, even when a patch of the universe contains no particles, the field is still there. Scalar fields are the simplest kinds of fields to exist. They just have a single value, a magnitude associated with every point in space-time. Every time you see a weather forecast with a map of temperatures across your local region, you are looking at a scalar field, a single number. In this case, a temperature associated with every point on the map. The eminent physicist Peter Higgs had already introduced a language of scalar fields decades before Guth, when he proposed what is now called the Higgs field, the scalar field working in the background of space-time that is responsible for mass. But now, it was Gauss's turn to invent a new scalar field that radically altered the dynamics of space-time in the distant past. The scalar field would permeate all of space and time, simply existing in the early universe. Then, randomly and suddenly, the scalar field would experience a dramatic phase transition, collapsing itself into a lower energy state. This collapse would provide the energy necessary to make the infant universe much, much bigger in a very short amount of time. Indeed, Gauss estimated that if the universe inflated by at least a factor of 10 to the power of 50 or so in less than a second, then all of those troublesome defects would simply be scattered to the four corners of the cosmos. While outside our observable limits, and as well as this, the process of a rapid inflation event would solve two other challenges of the traditional Big Bang model. It would explain why the universe could have a uniform temperature despite its enormous size, because prior to inflation, the cosmos homogenized, and why it appeared so flat. If you take any geometry you want to make it really, really big, then it will always appear flat to any local observers, just like the Earth appears flat in your garden. And so, because this idea of inflation so neatly explains several features of the observed universe, cosmologists began taking it seriously. And within a few years, Gauss's original idea evolved into the modern conception of inflation, first proposed independently by Andre Linder and the team of Andreas Albrecht and Paul Steinhardt. The quantum field didn't just suddenly jump to a new state, but instead slowly evolved into a lower energy state. It is a slow-roll inflation that allows the theory to put the bang in the Big Bang. At first, the inflation quantum field evolves into a lower energy state and powers the act of inflation. But at the end of this inflation, when the field is exhausted, the universe is large, cold, and empty. But this is where the magic of slow-roll inflation comes in. Through a process called reheating, at the end of inflation, the quantum field doesn't just sit still in its lowest energy state. Just like a ball that's rolled down a hill, the field wobbles a little. This wobbling transfers even more energy back into the cosmos, not in the form of super rapid accelerated expansion, but in the creation of particles. In quantum theory, this is allowed. Quantum fields transform and intermingle all the time. So in its dying breath, the quantum field responsible for inflation decays away, filling the universe with all the particles of everyday existence, the electrons, the photons, the neutrinos, and quarks, even the dark matter. And so, if there's anything that fits the popular conception of the Big Bang, inflation is it. Prior to this event, the universe was small, hot, and dense. When it was less than the tiniest fraction of a second old, however, inflation switched on in another tiniest fraction of a second. The cosmos exploded in size, and at the end of that stupendous expansion, the universe relit itself, suffused with energy from the inflation field, spawning the particles that continue to inhabit the modern-day universe. But while this model can handily explain many cosmological mysteries, that's not quite enough for it to rank as a true scientific theory at the same level of prestige as, say, general relativity or the germ theory of disease. Most importantly, when it comes to inflation, we have more questions than answers. We do not know the identity of the quantum field that drove it, for even if it survived to the present day, it would be just as a broken shadow of its former self, sitting well beyond our ability to detect it. We also don't know why inflation lasted as long as it did, or why it had just the right evolution to power super rapid expansion, then decay away, flooding the cosmos with particles. Some cosmologists argue that, due to these deficiencies, inflation is not a sound scientific theory. But the general concept of inflation, that a quantum field slowly evolved and triggered rapid expansion followed by a flood of particles, does make some generic predictions that are testable and in fact have been tested. The act of inflation didn't just rapidly expand the universe, it rapidly expanded all the tiny quantum foam that inhabits space-time. That quantum foam is submicroscopic, existing at the lowest level of reality. The incredible expansion of the cosmos under inflation turned that foam into still very small variations, but definitely bigger than they were, and this formed the seeds of structure. Tiny variations in space-time led to gravitational differences from place to place, and over time, these differences grew, eventually becoming the grandest structures in the universe. Generic theories of inflation, regardless of the precise mechanics of the model, predict very particular statistical properties of structure in the universe that we observe. And the cleanest way to measure those structures is through mapping the cosmic microwave background, the leftover light from when the universe was only 380,000 years old. One major test of inflation involves something called the Scalar Spectral Index. The map of the cosmic microwave background contains many variations, blotches of various sizes, representing colder and hotter parts of the cosmos. Cosmologists can turn this map into a spectrum, measuring how many large fluctuations there are, how many medium, and how many small. A scalar index of 1 would tell us that every size of fluctuation adds the same contribution to the general pattern. Inflation models generally predict a scalar index slightly less than 1, and in 2013, the Planck mission measured this number to be 0.96 to an accuracy of 5 sigma. The Planck satellite measured the exact statistical properties predicted by inflation, certainly a champagne-worthy event. And so, even though inflation sits beyond the edge of known physics, involving properties and forces and fields that we do not yet comprehend, most cosmologists believe that something like inflation happened in the early universe. While there are other hypothetical alternatives to the inflation story, in the end, they all tend to operate in much the same way: a rapid expansion of space, a flooding of particles, and the planting of the first seeds of structure. So, even if inflation turns out to be an incorrect theory of nature by all available evidence, the universe underwent something extraordinary in its earliest moments, something that gave rise to the Big Bang. But if inflation is correct, if there was some exotic quantum field that drove a super rapid expansion of space and ignited the Big Bang, then the theory has some intriguing implications. Because before the Big Bang, there was inflation, and before inflation, there was a never-ending stream of inflation. In this view, powered by cutting-edge theoretical physics, what we think of as our universe is just one in an infinite chain of universes, each one bubbling and branching off of a stream that will continue forever. Inflation always was and always will be. If this theory is correct, then what came before the Big Bang, before our universe, was the... In Fyodor Dostoevsky's 1846 novel The Double, a struggling young bureaucrat finds an unlikely companion, a man who looks exactly like him, except more fearful. At first, the two men are friends, but then the Double's charisma starts to take over the original's life. In the end, the original finds many copies of himself and is forced into an asylum. And though this is a fictional story, the concept behind it is not as far-fetched as it might seem. Because somewhere in a galaxy far, far away, there could be a copy of you, wearing the same clothes as you, the same age as you, the same life experiences, lovers, relatives as you, the same favorite restaurant and hated sports team. That copy of you, who also goes by the exact same name as you, could be watching a copy of this video right now. In parallel, the two of you watching it on exact duplicates of the screen, at the same point in the video, hearing the exact same information with the same voice. This copy will be inhabiting another universe, and this universe will be extremely distant from ours, far, far beyond the observable bounds of our cosmos. We could never access it, never travel there, and never exchange information with it, but it could exist, an exact replica, down to the subatomic level, and that copy would not be alone. Somewhere even more distant than the nearest copy would be another one, and another, and another. In fact, there would be an infinity of you all watching the same video in this precise moment. This is a reality of an infinite multiverse, a cosmos big enough to contain an infinity of universes, so large that it encompasses every possibility, every combination of molecule and atom and subatomic particle, and it copies each and every possibility an infinite number of times, both in the present and extending far into the future. The concept of a multiverse is staggering in its scope, but its tantalizing possibility is born in the fires before the Big Bang, in the event of inflation itself. One of the most vexing problems posed by inflation is just how it's supposed to stop to create just the right conditions for our universe. The quantum field powering inflation must slowly evolve to its lowest energy state and then finally come to rest. If the quantum field evolves too quickly, the universe expands too much, making a cosmos full of life impossible, and the end state, known as reheating, must also follow a particular path. Too much or too little energy injected back into the universe would render it desolate. To cosmologists, this seems very, very unlikely, oddly finely tuned, a strangely lucky coincidence. If the quantum field behaved any differently, even very slightly, then our universe would have just kept on rapidly expanding, never slowing down, never coming to rest, and never becoming populated with particles and fields and stars and galaxies. And so, this is where the concept of eternal inflation comes in. In this model, once inflation starts up in the infant universe, it just keeps going. The entire universe, in the broadest possible sense, keeps exploding, doubling over itself in a never-ending cascade of accelerated expansion, like a race car driver that never lets their foot off the pedal. The universe's expansion, once triggered in the first momentous act of inflation, never knows how to slow down. But this does mean that the universe is an ultimate beginning. Something had to kick off the first quantum field to start its journey towards inflation. So no matter what, the universe is a finite age in the past, but it can live forever into the future. There is always another part of the universe experiencing inflated growth on and on into infinity. Of course, we don't know if our universe, our inflation, our Big Bang was the first one, though it seems unlikely. And if not, what would have come before? Our inflation event was simply a previous one, and one before that, and so on back into the mist of time. But our observable universe is obviously not experiencing this kind of runaway growth. There is dark energy, and our cosmos is accelerating in its expansion, but compared to inflation, this is quite leisurely, not the kind of breakneck pace powered by these early quantum fields. So, how can we reconcile this observational fact with the concept of never-ending inflation? To make this work, physicist and inflation theory pioneer Paul Steinhardt proposed that our universe is just a tiny bubble, simply a piece of the much larger inflating space-time. In our tiny bubble, a portion of the inflation-driving quantum field settled into a low-energy state. Trapped there, that local condition caused our universe to separate itself, to pinch off from the wider cosmos. Here, inflation ended. Here, the portion of the quantum field behind inflation decayed away into the shower of particles and radiation that we see as the Big Bang. But not everywhere. Beyond the bounds of our universe, the rest of space-time continues to inflate, and out there, in that wider space-time, pieces of the quantum field continue to pinch off, separate, and settle down. Each time a portion pinches off, a new universe is born, with a new set of particles and radiation, a new realization of the cosmos. But, of course, this proposed multiverse wouldn't be infinitely big. However, it would quickly approach scales that might as well be. In just a single event of inflation, our universe already became 10 to the power of 50 times larger than its observable volume, and that was from a period of inflation lasting less than 10 to the power of negative 30 seconds. Imagine inflation lasting for an entire second, or a minute, or 10 billion years, or who knows how long since the initial spark. This is the inflationary multiverse, a giant, ever-growing collection of individual universes. Each universe is separated from the next by an almost uncountable number of light years, and that distance is growing because inflation causes space to expand faster than light. Each bubble universe is flying away from every other bubble universe faster than light. There can be no connections among them, no communication, no influence. And surprisingly, it is possible, at least in principle, to test this idea. Even though the other universes of the multiverse are unreachable, that collision would appear to us as a circle in the sky, a ring created at the intersection of our two bubbles. Many researchers have searched for these circles, both in maps of galaxies across the modern-day universe and within the cosmic microwave background. However, while there have been some intriguing hints of a signal, to date, nothing has withstood further scrutiny. This lack of detection does not rule out the multiverse idea, because there was only a slim chance, anyway, that our young universe would have intersected with another. But unfortunately, beyond that idea, there aren't really any rigorous ways to detect the existence of the multiverse. Since, by definition, the rest of the inflating universe exists beyond our observable horizon, impossible to reach. And it is because of this that many theoretical physicists have decried the idea of the multiverse, arguing that it's not a valid scientific theory. Indeed, among these are Paul Steinhardt himself. Even though he was one of the originators of the eternal inflation idea, he later turned to become a vocal critic of all inflation theories. After all, the multiverse fails to explain anything about our own particular universe. Within the multiverse, every possibility, every arrangement, and every combination of particles and forces is possible. That means there's nothing special about this particular arrangement that we find ourselves in, but there's also nothing special about any other arrangement. You simply can't tell from observations of your own universe whether the multiverse exists or not, which unfortunately isn't a very good way to build scientific theories. On top of this, it's also currently impossible to tell the potential variety of universes contained in the multiverse, as the details would depend on the exact physical mechanism that drove inflation in the first place, and when exactly inflation occurred. In the simplest scenario, the bubbles of the multiverse are just more universes, the same forces, fields, and particles that we're used to here, just in a variety of combinations. If we could visit another bubble universe, for example, we would see the familiar photons, gluons, quarks, and so on, and those particles would interact via the same forces that we have here. So, there would still be stars and galaxies in the cosmic web, just in a different pattern. But depending on what powers inflation, it's also possible that those universes could have different combinations of particles and forces, or even different fundamental constants. Different bubble universes could have different speeds of light, or different electron masses, or no electrons at all. Much of the physics that we take for granted could be totally different. Of course, most of those bubble universes would be completely inhospitable to life, or the formation of stars, or even macroscopic structures in general. But with so many universes, everything gets a chance. This is one of the strange features of such a large multiverse. And also, with infinite multiverse, there isn't just one occurrence of every single possibility. There are a huge number of occurrences of every single possibility. This means that there would be countless bubble universes where dark energy just rips everything apart before anything can form. There would be countless universes where light travels too slowly. There would be countless universes where electrons are the size of footballs, and there would be countless universes where everything is just fine, with the same kind of physics as we have in our universe. And the possibility of copies of you comes from the idea that there might only be a finite number of ways to combine all the matter in the universe. This idea is hypothetical, relying on our current understanding of quantum information. If it's true, and there really are only a limited number of ways that electrons, quarks, neutrinos, photons, and dark matter can position themselves in any universe, then with a large enough amount of bubble universes within the multiverse, each and every combination of particles wouldn't just appear once, but many, many, many times. The nature of the cosmos permits life to exist where the configurations of the extra dimensions allow just the right vibrations of strings to make stars, galaxies, and us. But even if we did know how to connect configurations of extra dimensions to vibrations of strings, we still wouldn't have a way to explain why our universe manifested in this particular way. Why did our universe choose this arrangement of dimensions instead of any of the others? This arrangement seems favorable to the development of intelligent life, at least as far as we understand it. But most of the others are presumably void, too big, too cold, too small, too weird. So, as string theorists began to develop the concept of the landscape, they kept running into this nasty Gordian knot. Why were these extra dimensions of our universe tied up in this particular way instead of any other? Was it just an accident? Or was there something more? And this is where eternal inflation could save the day. The landscape was a deeply hypothetical idea, a plane of possibilities mapping out every allowable universe. But it wasn't a thing. It wasn't a place that birthed new universes or a wider meta-universe. But eternal inflation and it implied multiverse, though also highly theoretical, were concrete, physical. In the 1990s, string theorists like Leonard Susskind and cosmologists like Andre Linde and Sam Martin IE got together. They realized that they were coming at the same problem from opposite directions. The cosmologists were trying to understand properties of our universe and hit upon the concept of a multiverse, that ours was just one of many. The string theorists were grappling with the possibility of an astounding number of possible universes, of which ours was just a single realization. Perhaps this was no mere coincidence. Perhaps there was something deeper going on. The string theorists could imagine the landscape, but didn't know how to create a universe from it. And yet here was the multiverse, a way that inflation naturally, effortlessly constructed every possible kind of cosmos. The multiverse idea, through eternal inflation, gives a physical mechanism to the string landscape. In other words, the multiverse could be how the string landscape manifests itself. Each new bubble universe can have its own set of physical laws, its own population of particles and energies and forces. Each one of those bubbly universes correspond to a singular point on the landscape, and each one of those universes is a sample of the possible configurations of the extra dimensions, a single chord on the instrument of the cosmos that vibrates its own unique set of frequencies. But as alluring as this concept is, as of right now, the connections between string theory and eternal inflation are tenuous at best. We do not fully understand the physics of inflation. Assuming that inflation even is a correct description of the extremely early universe, that means that we don't know how deep the multiverse goes, whether the bubble universes only sample different arrangements of the familiar forces or particles or manifest new configurations of the extra dimensions that lead to brand new physics. But the connection is attractive. Not only is our universe one of many, but over the span of creation, every possible manifold arises, every kind of possibility. This also saves string theory from the seemingly impossible task of having to explain why our universe has the properties it has, why it has this particular curling of extra dimensions instead of any other. With every possibility realized, with every kind of cosmos manufactured, we are guaranteed to find ourselves only in a universe that has a physics to make us possible. We are here, at this point in the string landscape, because we could not exist anywhere else. Those universes are out there, sampling every portion of the landscape countless times, but they are almost all empty and devoid of life. We are here in this one because it is the only universe that we can call home. This line of thinking is known as the anthropic argument, that the universe is the way it is because otherwise we wouldn't be here to observe it. And so, while it is the ultimate conclusion of the string landscape and multiverse ideas combined, many scientists argue that this line of thinking has led nowhere useful. We can't ever directly test the string landscape because, according to the string landscape, we were always going to arise anyway. We can't say why our universe has this configuration beyond that it is compatible with life. In response, some theorists have attempted to put the landscape on firmer grounds. For example, using some simplified calculations born from string theory, they hope to be able to say that the amount of dark matter or dark energy, or the mass of the electron, or any of the other parameters that make physics work the way we know it to work, are the most probable outcomes in the landscape. That kind of analysis won't erase worries over the anthropic argument, but it would at least ease some of the concern that our specific universe is so special and finely tuned. But, of course, again, this is all highly speculative. We don't know how or even if the string landscape connects to eternal inflation, but if it does, it offers a startlingly different view of our universe and the Big Bang. Before the Big Bang, there would be inflation. Before inflation, there would be eternal inflation and the multiverse. And before it all would be the string landscape. But not in the sense that the landscape is a physical entity. The idea is that before there was even the possibility of the cosmos, there was a reality of string theory in the landscape. With these rules in place, the universe could simply proceed evolving according to the machinations of strings and higher dimensions that manifested in the event of the first inflation, which began the race towards multiplicity. And from there, the separate bubble universes expanded and explored, discovering every nook and cranny of all possible string dimensions. But this extension of thought, where the ground is in string theory in the multiverse or some other theory of physics that we've yet to dream of, leads us back to the ultimate question. Why is there something rather than nothing? What created the string theory landscape? What came before the Big Bang? If the laws of physics made the universe, our cosmos, the multiverse, the landscape possible, then why are there laws of physics in the first place? Before, there was a time before your birth, and before you were born, before your mind organized itself into conscious awareness, before there was you. The universe still existed. The evidence is all around you, your parents, the memories and stories of older generations, photographs of mementos and monuments from before their time. Your birth may have been the beginning of you, but it was not the beginning of the world. And so, is this the case with our universe too, or our multiverse? We have seen that our cosmos may have ignited in a quantum fire known as inflation. That inflation event may not have been alone. It may be part of a never-ending string of eternal inflation, creating a grand cosmos that will continue inflating forever, and in the process, unfolding a multiverse of possible bubble universes. And that multiverse potentially solves the riddle of the string landscape, in the process explaining why our universe has the properties it does, to be amenable to life and intelligence. But though motivated by decades of research into theoretical physics, string theory still remains speculation. There is no experiment that has validated a theory, and indeed, because we lack the mathematical sophistication to tie together configurations of the extra dimensions with the vibrations of the strings, we actually can't test string theory. As powerful as its mathematics may be, it has not yet risen to the challenges that a proper physical theory must overcome. It cannot make predictions that can be tested against experiment. Even eternal inflation, while still on shaky ground, is at least motivated by a physical theory grounded in our current understanding of physics, the language of quantum fields. And most cosmologists strongly suspect something like inflation happened in the early universe. That said, there are other alternatives. The story of inflation, eternal inflation, and the string landscape is not the only approach to peering into the gray mist behind our Big Bang. In 2001, 4 physicists, Justin Seibert, Paul Steinhardt, and Neil Turok, proposed a completely different cosmological model, one that was still anchored in the latest thinking on string theory but without the need for inflation at all. In this model, before our universe, before what we would call the Big Bang, the cosmos was composed of giant floating brains. These brains are not biological networks, but the name given to cosmic strings that stretch over more than one dimension. In this model, our three-dimensional universe is one such gigantic brain, and it floats in an endless void of higher dimensional reality. Unfortunately, we cannot access these higher dimensions because the particles that make up our reality are restricted to live on this brain, and so our universe only appears three-dimensional. Long ago, this theory posits, before our Big Bang, the brain of our universe was cold, empty, and featureless. But it was not alone. There were other brains existing in the higher dimensional reality as well, and at some time, another brain collided with our own. The brains met at a point, releasing a storm of energy and triggering shock waves that rippled through them. From our perspective, embedded inside the brain, this looks like a Big Bang, a hot flash of energy at a singular point that floods the cosmos with particles and radiation, known as ekpyrotic cosmology. From the Greek word for fire, the model is able to reproduce the broad properties of our cosmos, the flatness, the lack of defects, the appearance of a Big Bang expansion, and even the formation of structures without invoking inflation and without building a multiverse. This ekpyrotic model also has one additional feature, the ability to reignite the cosmos. Our brain could collide again with another one in that higher dimensional space. That would start the process over again, igniting a fresh Big Bang. What we see as a singular event in our past is then just as regular and repeatable as a ball bouncing on the floor. And the ekpyrotic model isn't the only one that claims we live in a never-ending cycle of Big Bangs. Another approach to solving the riddle of Marian gravity with quantum mechanics, known as loop quantum gravity, suggests that what we see as a smooth and unbroken fabric of space-time is really a series of discrete elements, like the pixels of your computer screen. In our classical understanding of cosmology, rooted in general relativity, the universe begins as a singularity, a point of infinite density. But in loop quantum gravity, there's no such thing as the Big Bang. It is impossible to bring matter or space or time into a region smaller than the fundamental pixels of reality. When one attempts to do so, a pressure emerges that resists a collapse, the same way a spring gets hard to push the smaller you make it. So, when the universe collapses in on itself, it reaches a point where natural quantum reactions fling it back outwards, subverting the appearance of a singularity and igniting a new Big Bang in the process. And there are still more models and ideas that allow for creation of new universes, like Roger Penrose's conformal cyclic cosmology. In this model, in the extremely distant future, the universe is so thin, so cold, and so spread out that space and time are rendered meaningless, opening up the possibility of a new Big Bang springing to life. And so, whatever the case may be, the answer to the origins of our Big Bang, whether through inflation, string theory, loop quantum gravity, or something even more exotic, lies somewhere in the land of quantum gravity. We have to understand how gravity operates at extreme scales to push deep enough into our own past that we can understand the origins of our universe. We know that the singularity of general relativity, the infinitely tiny point at the beginning of our cosmos, is wrong. It is simply a sign that our mathematics is breaking down, and we need a new understanding. That new understanding may even require rewriting the definition of time itself. Our conception of the universe includes not just particles and radiation, not just forces and interactions, but the very fabric of space-time itself. Of course, We can envision a beginning to space, an imaginary spark that allows space to manifest and unfold itself, becoming the universe as we see it. But the beginning of time, how can there be cause and effect before the existence of time? How can the clock of our universe start before there was a clock? The beginning of the universe includes every feature of it, including time itself. So we can push the beginning of our universe beyond the edge of the Big Bang, into the realm of eternal inflation and the string landscape. But even in these most advanced and hypothetical ideas, there is still a start, still a beginning, still a time at which time begins. If this sounds like a paradox, it's because it is. There is much about time that we currently do not understand, and may never understand. So, what can we do? Our conceptions of time in physics are already muddled and contradictory. In quantum mechanics, time is treated as an external parameter, a fact of the universe that uniformly marches forward, allowing observers to make observations and for interactions to take place. Whereas in general relativity, time is fluid, relative, and tied into space through a harmonious fabric. To understand the universe, we must reconcile these perspectives. Very simply, we cannot speak confidently about a moment before time until we can understand with confidence what time exactly is. And so, for now, our thoughts on space and time aren't sophisticated enough to grapple with the beginning of it all. Because terms like begin are so rooted in our biological existence, so grounded in our fundamental conscious perspectives on the world around us, that we may not be able to escape our biases, even when we extend them to the farthest reaches of our most advanced theories. Indeed, the very process of time, the segregation of the past, present, and future, may break down in the early universe. This means it may ultimately be fruitless to search for an ultimate beginning before the Big Bang, because time itself, at least the way we currently grasp it, will become a useless framework for organizing the universe. And yet, even if we could surmount all these difficulties, that would still not be the end. Because no matter what, no matter which theory we propose to explain our own origins, whether an infinite chain of multiverse, or colliding brains, or an endless cycle of repeated Big Bangs, there is still something rather than nothing. There is still physics. There are still rules, laws, and ordered harmony that allow for the existence of the cosmos. If it's inflation, then there's a quantum field. If it's colliding brains or a landscape, then it's strings. If it's loop quantum gravity, then it's discrete units of space-time. And our voyages into the horizons beyond the beginning of the Big Bang will undoubtedly reveal even more rules, more structures, more laws that allow for the creation of laws. And so, whatever we find there, a fundamental reason that reality exists and may just be forever beyond us. You've been watching the entire history of the universe. Don't forget to like and subscribe, and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.